Gravity can pull you into a strand, a thread just one atom wide. That's spaghettification. It's a real process, not a story. It's what happens when you fall into a black hole. The universe bends space. It warps time. It creates forces you can't experience anywhere else. We're going to look at the edge of a black hole. We'll see the point where physics stops making sense, where the laws we know just break down. This is about seeing reality differently, not as a fixed stage, but as a fabric, something that can stretch, something that can twist, and something that can tear. So what does it feel like to approach the very end of space and the end of time? To feel that force, you'd have to be falling feet first. Your feet are a little closer to the core, so they feel a stronger pull than your head. It's a tiny difference in distance, but around a black hole, that tiny difference is everything. The pull on your feet gets fiercely stronger than the pull on your head, so you start to stretch, not like a rubber band. It's a steady, relentless pull. And at the same time, the sides of your body get squeezed inward, like the universe is giving you a cosmic hug from all sides, compressing you toward your center. That's the two-part process, spaghettification. You're pulled long and thin like taffy, while also being crushed into a narrower strand. The name comes from that final shape, a long, thin thread of what was once a person or a planet. But the science behind it is brutally precise. It's formally called tidal disruption. Think of ocean tides on Earth. The moon's gravity pulls more strongly on the side of the planet facing it, stretching the global ocean slightly. Now take that gentle, watery bulge and amplify it by billions. Replace the moon's gentle tug with the bottomless hunger of a black hole. That's the tidal force. The difference in gravity across an object taken to its most violent extreme. It's not about being crushed by uniform pressure like deep underwater. It's about being pulled apart by a difference. Your own body becomes a battleground between two slightly different strengths of gravity, and the stronger one always wins. So while the term might bring a smile, it describes a fundamental truth about how gravity warps reality. It transforms a solid object into a stream of atoms, a single file line of matter falling toward the impossible. Understanding that this cosmic noodle-making is the essential first step. It turns a cartoonish idea into a serious key for unlocking the strange physics waiting at the edge of everything we know. So gravity isn't just a pull, it's not like a string, it's more like a slope. A curve in the fabric of the universe. That's the core of Einstein's idea. Gravity is the shape of space and time together. They call it spacetime. Think of a trampoline. You put a heavy ball in the middle, it makes a deep well. A marble rolls in not because it's pulled, but because it's following the curve. A star or a black hole does that to space-time. It makes a well so deep that light can't escape once it goes in. Around our sun, that curve is gentle, a wide, shallow slope, but around a black hole, the well becomes a pit. The sides get incredibly steep, and that steepness is what changes everything. It's the difference between orbiting and being stretched apart. Physicists have a name for that steepness. The gravitational gradient. It's how much the pull of gravity changes over a distance. We actually feel a small version of this already with the moon and the tides. The moon's gravity pulls harder on the side of Earth facing it. That stretches the ocean, makes a bulge, high tide. On the far side, the water is left behind, so there's another bulge. That stretching is a tidal force. It's the difference in pull from one side of the planet to the other. For Earth, it's just a gentle, rhythmic push and pull. Now take that idea and amplify it beyond anything. Bring it to a black hole. There, the gradient isn't a slope, it's a cliff. Over just the meter from your head to your feet, the strength of gravity doesn't change a little. It changes by billions of times. Your feet are pulled with impossible force. Your head is pulled slightly less. That difference is the tidal force, and at that scale, it's not a nudge anymore. It becomes the main force. It overpowers the forces that hold your atoms together. It beats the forces that bind your molecules. Kip Thorne explained this. These tidal forces near a compact object are so extreme they can distort and disrupt anything. That's why black holes are the ultimate poster makers. No other object has so much mass in such a tiny point. It creates a gradient that's unimaginably steep. To fall toward one is to enter a place where being a solid object stops making sense. You're not being pulled down. You're being unraveled by the shape of space itself. That final break, though, it doesn't always happen right at the threshold. You cross a line you can't see. The event horizon, it's not a wall of fire or rock. It's a boundary in the fabric of the universe, a point where the slope of spacetime gets so steep that all paths, even light's path, curve inward forever. The ultimate one-way door. From our view, watching from a safe distance, that's where you'd seem to freeze. Your image reddens and fades, stretched by time into a final, ghostly snapshot. But for you, falling, nothing special happens then. No flash, no jolt, no sudden tearing. You just pass from a place where escape was theoretically possible to a place where it absolutely isn't. The universe quietly closes its door behind you. That's the strange truth about the event horizon. It's defined by geometry, not by a sudden physical force. The tidal stretching, the spaghettification, that's a separate thing. It doesn't depend on this invisible boundary. It depends on the steepness of the gravitational slope beneath your feet. And that steepness is determined by one thing above all else: the size of the black hole. For a small, stellar mass black hole, the horizon is just miles across. The gravitational cliff is so sharp, so close to the core, that the tidal forces are overwhelming. You'd be stretched apart long before you ever reached the point of no return. The horizon would be the last thing your scattered atoms passed through. But for a supermassive black hole like the one at the center of our galaxy, the story is different. Profoundly different. These are cosmic giants, event horizons that could swallow our solar system whole. Their mass is so vast, spread over such a colossal volume, that the slope of spacetime near the horizon can be surprisingly gentle. You could cross that one-way boundary feeling nothing unusual at all. The difference in gravity between your head and your feet might be no more severe than what you feel standing on Earth. You'd float past the horizon intact, unaware you'd just made the most irreversible decision in the universe. Your spaghettification, your unraveling, would wait for you much deeper inside. Where the slope finally becomes impossibly steep, this separation between the coordinate of the horizon and the physical sensation of tidal force, that's a crucial pivot. It means your journey's character, its duration, its final moments are written not by the door you walk through, but by the size of the room you're entering. The size of a black hole changes everything. It's the difference between a steep cliff and a long, gentle slope. A stellar mass black hole comes from a collapsed star. It's surprisingly small. Its event horizon, the Schwarzschild radius, might only be a few miles across. All that gravity is packed into a tiny point. So the slope of spacetime right there is incredibly sharp. The tidal forces become overwhelming long before you reach the point of no return. For something this small, the zone where you get stretched into a strand lies well outside the event horizon. It's like approaching a waterfall. You feel the current pulling at you, pulling you apart, long before you ever go over the edge. The physics is clear. The tidal force you feel is inversely proportional to the cube of the black hole's mass. Double the mass, and the stretching force at the horizon becomes 8 times weaker. So for a small black hole with a mass of just a few suns, that force is astronomically strong. It would pull you into a strand while you were still thousands of miles away. From the outside watching, your final moments would be a swift, violent change. Now consider the supermassive black hole at the center of our galaxy, Sagittarius, a star. It has a mass millions of times greater than our Sun. That mass isn't denser, it's just more of it, spread over a much larger volume. Its event horizon isn't miles across. It's millions of miles across, a sphere so large it could contain our entire solar system. Because all that mass is so spread out, the slope of spacetime at the horizon is remarkably gentle. The gravitational gradient is shallow. You could cross that one-way boundary, the event horizon, and feel nothing more than a mild tide, no sudden rip. No dramatic stretch, you'd be intact, floating into the darkness. You might not even realize the moment you pass the point of no return. The spaghettification process still happens, but it lies far ahead, deep in the interior where spacetime finally curves into that impossible steepness. This journey isn't a sudden snap, it's a slow, inevitable sinking. To picture this, think of two ways to cross a finish line. One is like sprinting directly into a brick wall. The impact is immediate and total. That's the stellar mass experience. The other is like wading into a sea of thick, black tar. You cross the line smoothly, but then the substance slowly envelops you, pulling you down over a much longer time. That's the supermassive story. One gives you a catastrophic end right at the door. The other gives you a deceptive, quiet passage, with the true unraveling waiting patiently in the depths. This comparison changes how we imagine these things. It tells us that the most massive black holes might be the only places where you could, theoretically, witness the interior and survive long enough to even process it. Survival is ultimately impossible, but the journey there, the story of your final moments, is written in the numbers, in the difference between a cliff and a slope. And that leads to a question. If you could cross the horizon of a giant black hole intact, what would you actually see? What unfolds in that strange darkness between the door and the end? The pull of gravity weakens with distance. That's just how it works, but near a black hole, distances get compressed, forces get magnified. Your feet are a little closer to the singularity than your head. So they feel a stronger tug. That difference in force is the radial tidal force. That's what pulls you long. To picture it, imagine your body as a series of balls connected by springs. The springs are the chemical bonds holding your atoms together. They have a certain strength. Now drop that model feet first toward the black hole. The ball for your feet feels the strongest pull. It starts accelerating faster than the ball for your head. The spring between them stretches. If the difference in pull is gentle, the spring stretches a little but holds. But if the difference is enormous, the spring stretches past its limit. It snaps. Now scale that up. Every molecular bond in your body is like that spring. The tidal force doesn't just stretch you as a whole. It works on every layer, pulling each atom away from its neighbor, and that force grows unstoppably. The math behind this is severe in its elegance. The stretching force is proportional to the black hole's mass, but it's inversely proportional to the cube of your distance from it. That cubic relationship is key. It means as you get closer, the stretching doesn't just increase. It explodes, move twice as close, and the tidal force becomes 8 times stronger. That's why the final moments near a small black hole are so catastrophically swift. We see a gentler version of this throughout the cosmos. It's called the Roche limit. Every planet or star has one. It's the minimum distance a smaller object, like a moon, can approach before the difference in gravity across it becomes stronger than its own self-gravity. Inside this limit, the object is pulled apart. Saturn's rings are an example. They likely formed from a moon or comet that wandered too close. It crossed Saturn's Roche limit and was tidally shredded into fragments. For a planet, that limit is a zone of disruption. For a black hole, the concept is taken to its extreme. The black hole's Roche limit isn't a zone you might cross. It's an inevitable wall you hit on the way in. And because the gravity is so intense, the forces aren't just overcoming an object's weak gravitational hold on itself. They're overcoming the powerful electromagnetic forces that bind solid matter. This is the ultimate tidal disruption. It reduces everything, a moon of ice, a being of flesh and bone, to the same basic state. A stream of fundamental particles, all following the same inescapable curve. Understanding this pull, this radial stretching, gives us the first half of the picture. It explains the lengthening, but to become a strand, you also have to get thinner. Lengthening is only half of it. At the same time you're being pulled long, you're also being crushed thin. That's the squeeze. Gravity pulls everything toward a single point. So imagine a crowd rushing toward a small door. The people in front of you and behind you, they get pulled ahead or held back. That stretches the line you're in. That's the radial stretch. But the people to your left and right are also being pulled toward that same point. They converge inward, pressing against you from both sides. That's the lateral compression. With a black hole, your body is that crowd. Every atom in you is being pulled toward the center. The atoms along your sides aren't pulled straight down, they're pulled on a diagonal inward. That creates a squeezing force perpendicular to your fall. It crushes you from all sides toward your own center line. Picture a spherical cloud of dust falling in. First, the radial stretching starts. It pulls the cloud into an oval like a football, but at the same time, the lateral compression acts from all directions. The sides of the oval get pushed inward. The football shape gets squeezed into a pancake, but the stretching never stops, so the pancake, now thinner, keeps being pulled long. The combination is relentless. The pancake narrows further, its edges streaming toward the center line, until the whole cloud becomes a single, thin filament. A strand. This two-axis deformation is why the outcome isn't just a stretched rope, which still has some thickness. It's spaghetti. The lateral forces make you fundamentally one-dimensional. We can feel a whisper of this here on Earth, though it's immeasurably faint. The same moon that creates ocean tides also very slightly compresses the solid Earth from the sides. Our planet isn't a perfect sphere, it's an oblate spheroid, slightly squashed at the poles. That's mostly from its rotation, but tidal forces from the sun and moon add a tiny, constant pressure. It's a harmony of forces, a gentle push and pull that shapes worlds over eons. At a black hole, that harmony becomes a crescendo. The lateral compression isn't gentle pressure. It's a violent, instantaneous collapse inward. It happens at the same atomic level as the stretching. As the bonds between your molecules are pulled long, the structure is also being crushed from the sides, removing any volume, any breadth, any space that once made you a solid thing. So the journey to becoming a strand is a precise physical ballet, a dreadful symmetry. You are pulled apart along one axis and crushed together along the other two. What emerges isn't debris, not dust. It's a streamlined thread of elementary particles. All individuality of structure is erased, reduced to a sequence in a single file line. This complete picture, the stretch and the squeeze, shows something about gravity's nature. It doesn't just attract, it sculpts. It takes the complex and renders it simple. It takes the three-dimensional and reduces it to one. And in that final, thin line of atoms streaming into the dark, you see the ultimate signature of a law that tolerates no complexity at its core. But then that raises a deeper question. What becomes of the information that was you? The arrangement of atoms that held your memories, your thoughts, the pattern of your being. When that pattern is shredded into a linear sequence, is it lost forever? Or does the universe, in some strange way, keep a receipt? That final unraveling has a precise location. We can calculate exactly where it starts. It's called the tidal disruption radius, the point where the stretching force exceeds what's holding you together. It's not the event horizon, It's a line drawn in space, unique for every black hole and whatever's falling in. To find it, you look at the equation for tidal force. The tidal acceleration, the difference in pull between 2 points, it's proportional to the black hole's mass multiplied by the length of the object divided by the cube of the distance from the center. It sounds complex, but each piece has a meaning. The mass m is the source of the curve in spacetime. The length L is the scale, the distance from your head to your feet. And the distance r is how close you are to the center. That r-cubed term in the denominator is the key. Because it's cubed, the force doesn't just increase as you get closer. It skyrockets, halve your distance, and the force becomes 8 times stronger. That's why approaching feels calm at first, then turns catastrophic. The cliff is exponentially steep. Put numbers to it: a stellar mass black hole 10 times the sun's mass. For a human, roughly 2 meters tall, the tidal disruption radius is thousands of kilometers out. You'd be spaghettified far outside the event horizon, which for this black hole is only about 30 kilometers across. The math is clear. You cease to be you long before the point of no return. Now take a more rigid object, a solid metal spacecraft. Its structural integrity is far greater than the chemical bonds in a body. For that same black hole, the spacecraft's disruption radius would be much smaller. It could venture closer before the metal groans and tears. It might even cross the event horizon intact, only to be shredded inside. This comparison shows something. Survival isn't just about the black hole. It's about what you're made of. A diamond with its strong atomic lattice could plunge deeper toward a small black hole than a human. But no known material can withstand the tidal forces at the horizon of a stellar mass remnant. The equation is unforgiving. This framework does more than predict destruction. It lets us map the anatomy of a black hole's influence, draw concentric spheres around it, the outermost where a gas cloud begins to stretch, closer in, the radius where a planet is torn apart. Closer still, where a star is shredded. Astronomers have seen this as a brilliant flare. And deepest of all, for a small black hole, the line where a human form dissolves into a stream of atoms. Each boundary is a tide mark, a record of gravity's power over a specific structure. Understanding this shifts the view from a black hole as a vacuum cleaner to an architect of transformation. The end is not a single moment. It's a process with a calculable beginning. And if we can calculate where cohesion fails, it makes you wonder, what lies beyond that failure? What is the final state of that stream of particles? Do they vanish at the singularity, or does the story take another turn? Physics gives us equations, not experiences. To cross that chasm, you have to shift perspective, from the outside observer to the one falling in. So let's follow a thought experiment. An astronaut named Alex on a one-way trajectory toward a stellar mass black hole. The ship is gone, lost to a malfunction. Only the suit remains and the quiet hum of its life support. At first, the fall feels like floating. No up or down, just the serene drift toward a perfect circle of darkness ahead. The sensation begins subtly, a faint tug at the boots, not pain but a persistent pressure like a gentle current pulling at your feet. That's the first whisper of the tidal gradient. As minutes pass, that tug intensifies into a firm, steady pull. Alex feels a growing tension, a sense of being drawn taut from head to toe. It's a stretching sensation deep in the bones. The suit's fabric, designed for the vacuum of space, begins to strain at the seams. Inside the helmet, vision starts to warp. The black hole ahead doesn't just grow larger. It stretches vertically, becoming a thin, dark slit in the starfield. The stars themselves smear into streaks of light, pulled into lines pointing toward the center. That's the universe itself distorting, the paths of light bending around you. The tension builds past discomfort. It becomes a profound, inescapable force. The body is not built for this. tendons and ligaments, muscles and blood vessels, all subjected to a differential pull they cannot resist. The spine would feel at first a deep internal elongation. Neurologists suggest the brain would be flooded with novel, catastrophic sensory input. Proprioception, the sense of where your body is in space, would break down entirely, reporting impossible data. The feeling might be interpreted not as a sharp pain, but as an overwhelming, all-consuming pressure, a profound sense of bodily distortion, a terrifying wrongness the mind has no framework to process. The final moments are not explosive, but a failure of integrity. At the atomic level, the molecular bonds that give structure to flesh and bone are overcome. The body ceases to function as a cohesive whole. It yields, transitioning from a person into a stream of matter. The thought experiment ends there, at the limit of experience. It highlights the unbridgeable gap between the clean lines of a tidal force equation and the visceral, biological reality of that force. This chasm is central to black hole physics. We can calculate the radius of disruption to the meter. We can model the stream of particles, but the subjective reality of that transformation remains forever outside our science. A reminder that some predictions are maps of a territory we can never truly walk. The human body is fragile. It's bound by chemistry and biology, but the laws of physics don't discriminate. They apply to steel the same way they apply to flesh. So you have to ask what happens to our greatest creations, a deep space probe, forged from titanium and composite alloys. Its hull is designed to withstand solar flares, micrometeoroid impacts. It's the pinnacle of our material science, but if you send it toward a stellar mass black hole, it fares no better in the end. Its fate is written by the same tidal equation, only the numbers are slightly different. The key is tensile strength. That's the maximum stress a material can take while being stretched before it fails. For the human body, that strength is measured in megapascals, and it's quite low. For aerospace-grade titanium, it's orders of magnitude higher. That means the probe's tidal disruption radius is much smaller. It can venture far closer to the black hole's core before the stretching force exceeds the atomic bonds holding its hull together. It might even cross the event horizon of a small black hole still in one piece. An astronaut could never do that, but this isn't salvation. It's just a postponement. Once inside, the forces keep growing, exponentially. No known alloy, no diamondoid lattice, no theoretical metamaterial we can conceive has a tensile strength high enough to withstand the tidal forces near the singularity. The metal will yield, it will groan, then elongate. Its molecular structure gets pulled into alignment with the gravitational current. It becomes a strand of refined ore. Then a stream of individual atoms following the same inescapable path. Long before that physical tearing, though, the probe's functionality would be destroyed. Its complex inner world of circuitry and electromagnetic fields is even more vulnerable. The tidal forces don't just act on mass, they act on spacetime itself. This warping induces monstrous stresses in the probe's internal electrical systems. Think about the delicate pathways on a computer chip, printed at the nanometer scale. A differential stretch across that chip, even a microscopic one, ruptures those pathways instantly. The organized flow of electrons that constitutes computation dissolves into chaos. Sensors feed back nonsense data as the very fabric of space they're measuring distorts around them. Power systems fail as magnetic fields are twisted and contorted. The probe goes dark, a silent, dead shell, well before its hull begins to visibly deform. Its death is a layered process, first the mind, then the body. This principle extends to any object, a wandering asteroid of solid iron, a fragment of a shattered white dwarf star made of crystallized carbon. Under the tidal dominion of a black hole, their immense material strength is irrelevant. They are all, in the end, just collections of particles, And in that environment, the force that pulls them apart grows faster than any force that holds them together. The outcome is universal. The asteroid becomes a stream of iron atoms. The diamond shard becomes a filament of carbon. All complexity, all history etched into their structure is erased. They are reduced to their most basic linear form. This expansion from the biological to the technological and geological makes the physics clear. Spaghettification isn't a grotesque fate reserved for life. It's the universal signature of a law. Gravity, in its most extreme expression, is a great simplifier. It strips away hierarchy and sophistication. It reduces the universe's most intricate constructions to the same singular state. A one-dimensional flow of fundamental ingredients. Our machines, our monuments, even entire worlds, all share the same ultimate vulnerability to the curve of spacetime. And if that's true for all matter we know, it forces a more radical question. What about the things we cannot see? What happens to light itself, or to the very information that seemed to be lost in that stream of atoms? Does anything truly escape this simplification? Or is there a deeper ledger being kept? The physics that stretches a human into a strand, that same physics works on a cosmic scale every day. It happens to these vast clouds of gas and dust. They don't fall straight in. They have a slight sideways motion, so the black hole's gravity seizes them, forces them into a spiral. As the cloud spirals inward, it gets caught in the tidal forces. The side closer is pulled harder than the far side, and that stretches the whole cloud. It becomes a long, thin streamer, spaghettification, but for a celestial fog bank. Then you get multiple streams pulled from different directions. They collide, they tangle, they don't just vanish, they form a structure we can actually see from across the universe. An accretion disk, a vast, flat, churning whirlpool of superheated matter, orbiting at nearly the speed of light. This is where the violence turns into light. The particles in this disk, these spaghettified streams, they're not moving in harmony. They rub against each other, unimaginable force, the most extreme friction you can think of. That friction, along with the immense magnetic fields from the swirling plasma, it converts the kinetic energy of the fall into heat. Temperatures soar to millions of degrees. The disk doesn't just glow, it screams across the electromagnetic spectrum. It emits torrents of X-rays, gamma rays, a brilliant beacon of high-energy radiation. That's how we find black holes that aren't completely isolated. We don't see the darkness, we see the fiery shredder around it, but the accretion disk is more than a light show. It's the engine of growth. Some of this spiraling, superheated matter loses energy through radiation and friction. It can't maintain its orbit anymore. So it crosses the event horizon. It feeds the black hole's mass. The rest gets funneled away by magnetic fields. It forms powerful jets that blast out from the poles. They shoot across thousands of light years. These jets can shape entire galaxies. They heat interstellar gas. They regulate star formation. So the process that tidally shreds a star or a person is the same one that powers the most luminous objects in the cosmos. Spaghettification isn't a quiet end. It's an ongoing, energetic process, a fundamental part of how black holes interact with their environment, how they control it. The cosmic shredder is also a cosmic forge, and its light, that's the signature of gravity doing its most extreme work. The story of falling happens in two different times. There's the time for the person falling, and then there's the time for everyone else watching. And this is where Einstein's relativity can't be ignored. Gravity bends space, but it also stretches time. Near a black hole, that stretching becomes absolute. If you're watching from a safe distance, you see something bizarre happen to the image of the falling astronaut. As they get close to the event horizon, their clock seems to tick slower. Their movements decelerate into this infinite slow motion. the light from them reddens and dims and finally fades from view. From that distant perspective, the astronaut never quite crosses the horizon. They appear to freeze there like a ghostly fossil etched onto the edge of forever. That's the famous effect, frozen at the horizon. It's a real prediction from the equations, but it's an illusion of perspective. It's a trick of the light struggling to climb out of an infinitely deep gravitational well. For the astronaut falling, time passes normally. Their watch ticks second by second. The horizon isn't a wall of light or a frozen snapshot. It's a coordinate in space they pass through without any fanfare. And the spaghettification process, from their point of view, happens according to the local tidal forces. For a stellar mass black hole, it would be swift, catastrophic at a specific moment. For a supermassive one, it might be a gradual, drawn-out sensation deep in the interior. But here's the profound paradox. From the outside, that entire process, the stretching, the transformation into a strand, would appear to happen in extreme slow motion. It would be stretched across an unimaginable span of external time. The moment the atomic bonds break from our safe vantage point might be dilated across centuries or millennia or even longer. We would see it as a gradual, creeping distortion. A spectral figure slowly elongating and thinning over cosmic eons. This intertwining of space and time means spaghettification isn't just a physical event with a location. It's a space-time event. Its when depends entirely on who is asking. For the falling individual, it has a local time stamp. For the universe at large, it is smeared across an infinite timeline. It becomes a permanent, fading feature of the black hole's visual history. This temporal distortion adds a layer of profound strangeness. It means the most violent physical transformation can appear from a distance as a state of eerie, suspended animation. The universe records the event not as a sudden snap, but as an endless sigh. It forces us to accept that near these objects, our common sense notions of now and then completely unravel. Two realities, both valid, describe the same fate in irreconcilable ways. One is intimate, local, and final. The other is distant, eternal, and ghostly. So which one is real? According to relativity, the answer is both. The falling observer's experience is real for them. The frozen image is real for us. That's the true heart of the paradox. It's not a contradiction. It's a demonstration that reality itself is frame-dependent. Our instinct to find a single, objective story breaks down at the horizon. And in that breakdown, we see the universe operating by a deeper, more interconnected set of rules, where time isn't a universal river, but a personal, malleable experience shaped by gravity's touch. Our picture of gravity starts with Newton. An apple falls, the moon goes around. It's a force that pulls at a distance. For most things planning a satellite's orbit, sending a probe to Mars, Newton's laws work perfectly. They even give us a first, rough idea of tides. That difference in pull. Newton's math says the tidal stretching force is proportional to the black hole's mass and inversely proportional to the cube of your distance. It's a clean prediction. If you used it to calculate what happens near a stellar mass black hole, it would say you get pulled apart. But that Newtonian story isn't complete. It's a shadow on the wall, missing the shape of the thing casting it. When you get close to a black hole's extreme gravity, Newton's framework breaks down. Catastrophically, it breaks because it treats gravity as a simple force acting across a fixed stage of space and time. It doesn't know that mass and energy warp the stage itself. That space can curve, time can stretch. That's where Einstein's general relativity takes over. It's not a correction to Newton, it's a reinvention. Gravity isn't a force in the traditional sense. It's the geometry of spacetime, and if you recalculate tidal forces using Einstein's equations, you get a different answer, a profoundly different one. especially near the event horizon. For a non-spinning black hole, a Schwarzschild black hole, the difference is stark. Newton says the tidal force grows without bound as you approach the center. It becomes infinite. Einstein's relativity tells a more nuanced story. The tidal force does increase as you fall in, but it reaches a maximum at a specific point outside the event horizon. And then, counterintuitively, it starts to decrease as you keep falling toward the singularity. It doesn't vanish, but it changes. The stretching force along your body actually lessens, while the lateral crushing force from the sides becomes dominant. Newtonian physics could never predict that. It's a signature of spacetime curvature. The geometry itself is doing something more complex than a simple pull. For the most realistic black holes, the spinning ones, Kerr black holes, the divergence is even more dramatic. A spinning black hole drags spacetime around with it. That's frame dragging. This rotation twists the gravitational field. The tidal forces near a Kerr black hole aren't symmetric. They become complex, oscillating. They can stretch and squeeze you in alternating patterns as you fall. Newton's simple, radial pull can't account for this cosmic whirlpool. His equations would be silent on it. Seeing this boundary where one great theory yields to another isn't just academic. It's key to understanding why black holes are the ultimate laboratories. They're places where our classical, intuitive understanding of the universe is stress-tested to the breaking point. They force us to use the most advanced math, the most radical concepts. They show us where our maps of reality end and where the true, uncharted territory begins. To study a black hole is to stand at the edge of known physics, looking into a realm where gravity isn't a force, but the architect of reality. And if our understanding of something as basic as a tidal force has to be rewritten there, it raises a deeper question. What other intuitions do we have to surrender to really see what's inside? Einstein's vision changed gravity. It wasn't a force anymore. It became a property of the stage. The stage is space-time, and you can think of it as a fabric. A flexible fabric. The common picture is a rubber sheet. You put a heavy ball in the middle, it makes a dip. Roll a marble near it, and the marble spirals in. It's not being pulled, it's just following the curve. That's a helpful start, but it's incomplete. The sheet only shows space warping, and it needs an outside gravity to make the ball sink. But in reality, the mass is the warp. It curves space and time together into a four-dimensional shape, a shape we can't really see. To move through this curved landscape, objects follow paths. They're called geodesics. A geodesic is the straightest possible line in a curved geometry. On Earth, a great circle route for a plane, that's a geodesic. It's the shortest distance, even though it looks curved on a map. In flat, empty spacetime, a geodesic is a straight line, constant speed, but near a planet, spacetime is curved. So the geodesics become orbits. They become the arcs of falling objects. An astronaut in freefall from their own view is just following a geodesic. They feel weightless because they're moving along the straightest path available in the curved geometry around them. This is where the geometry of spaghettification gets clear. Your body isn't a single point, it has extension. When you fall toward a black hole, your head and your feet are on slightly different trajectories through spacetime. They're trying to follow two distinct geodesics, neighboring geodesics. In the gentle curve of Earth's gravity, those two paths are almost parallel. Your head and feet fall together. You keep your shape, but in the sharp curvature near a black hole, those initially close geodesics diverge. Rapidly, they pull away from each other as they plunge toward the center. Imagine two ants side by side on a deflated balloon. Now imagine the balloon inflates rapidly right beneath them. As the rubber stretches, the two ants, each trying to walk a straight line, are carried apart. They aren't being pushed. The geometry beneath them is changing. That's tidal stretching. Your feet, on a geodesic through a region of more extreme curvature, accelerate away from your head. Your head is on a geodesic through a slightly less curved region. The lateral compression happens for the same geometric reason. Geodesics from the sides of your body all converge inward. Like lines of longitude meeting at a pole, so spaghettification isn't a force, not in the Newtonian sense. It's not something reaching out to grab you. It's the inevitable geometric result, an extended object trying to travel along wildly diverging straight lines. In a deeply warped universe, the rubber sheet tears in the analogy. But in reality, it's the paths themselves that split apart. This reframing is profound. It shifts the language from action at a distance to passive geometry. You aren't being pulled apart. You are coming apart because the very definition of straight ahead for your feet is radically different than it is for your head. In that difference lies the transformation from a person into a strand, not by force, but by the unforgiving contours of reality itself. A Schwarzschild black hole is the simple case. It doesn't spin, but reality is more dynamic. Most black holes are probably spinning, and that rotation changes everything. They're described by a different solution, the Kerr metric, named for Roy Kerr. In this model, the black hole isn't a static pit. It's a cosmic whirlpool, and it drags spacetime around with it. That creates a region outside the event horizon called the ergosphere. A zone of twisted spacetime where nothing can stand still, not even light. All matter and energy is forced to move, swept along with the spin. It's like being caught in a river with a current so strong you can't paddle against it. You're compelled to go with the flow of space itself. This rotation changes the tidal forces you'd feel. In a non-spinning hole, spaghettification is symmetrical. The stretch is along your length, the squeeze is uniform from the sides, but with spin, the geometry becomes lopsided. The forces aren't the same in all directions. If you fall in along the equator, moving with the spin, the frame dragging can actually moderate the stretching. It's like a helping current that carries you along, reducing the pull between your head and your feet. But if you try to fall in against the spin or from over the poles, the forces become more intense, more complex. You might feel a twisting, oscillating pull, a stretch in one direction, then a crushing pressure from another. The process becomes asymmetrical, less like being pulled into a clean strand, more like being wrung out by an invisible, cosmic hand. The interior changes even more. In the simple model, the singularity is a point of infinite density at the center, a place where all paths end. In a Kerr black hole, the math suggests the singularity isn't a point but a ring. A one-dimensional loop of infinite density, and that's not just a shape change. It opens up bizarre possibilities. Some solutions to the equations suggest that, if you could survive, you might pass through the ring. Not into another part of our universe, but into a region of spacetime with entirely different properties. A place where time could behave like space, and travel might become possible in ways we can't comprehend. Of course, nothing material could survive that. The tidal forces near the ring singularity would be unimaginably violent, chaotic. But the existence of this structure shows how rotation injects a profound complexity into the heart of darkness. This diversity, from the simple Schwarzschild pit to the whirling Kerr maelstrom, shows a crucial truth. Black holes aren't all the same. Their size, their spin, their charge, they create a rich family of objects. And that means the story of falling, the specific narrative of spaghettification, has many possible chapters. It could be a swift, symmetrical snap, or a drawn-out, twisting unraveling. It depends on the specific monster you approach. This complexity moves them from being simple cosmic vacuum cleaners to dynamic engines, sculpted by the same physics that govern spinning tops and swirling galaxies. Their rotation is a memory of their birth, a final momentum from the collapsing star that forged them. And it's that spin which paints their final portrait, dictating the strange and varied ways they reshape everything that comes too close. That last line of atoms, it's carrying information. Every particle, every bond, every twist in a DNA spiral. It's all data. Data about what the thing was, where it came from, its whole history. In our normal world, information seems durable. You can burn a book, but if you could track every ash particle, every trace of smoke, you could reconstruct the text. The information is transformed, not destroyed. That's a bedrock principle in quantum mechanics, unitarity. Information has to be conserved, but a black hole, and the spaghettification that feeds it, challenges that directly. When something gets tidally shredded into a one-dimensional stream, its complex structure is obliterated. All that intricate information about its shape, its composition, its past. It gets scrambled, it seems to turn into pure randomness. Then that stream crosses the event horizon, and it's lost to our universe forever. According to classical general relativity, the information is just gone. Erased, that's the black hole information paradox. Quantum mechanics says information can't be destroyed. Einstein's theory of gravity, combined with this violent process, suggests it is. For decades, that was a glaring contradiction, a sign our understanding of reality was incomplete, right where gravity meets the quantum world. Theorists like Leonard Susskind proposed a way out. Black hole complementarity. The idea is the information isn't destroyed inside. Instead, it's preserved on the two-dimensional surface of the event horizon itself. From the outside, watching the frozen, red-shifted image of something falling in, all the information about that object gets smeared onto this surface. Like a hologram, from the perspective of the thing falling in, it passes smoothly through the horizon. Information intact. Both stories can be true because no single observer can ever have both perspectives. That leads to something even more profound, the holographic principle. It suggests all the information describing a three-dimensional volume of space, like the inside of a black hole, can be fully represented on its two-dimensional boundary. The universe might fundamentally be a hologram. So for our spaghettified astronaut, it means while their physical form is utterly transformed by tidal forces, the information that constituted them might not vanish. It could be transferred, in some vastly complex code, onto the shimmering surface of the horizon. Their story isn't deleted, it's translated, printed onto the fabric of spacetime at the edge of the abyss. This connection turns a dramatic physical process into a gateway, a deep philosophical question. What is reality, if the information that defines it can exist in two such different forms? One, a three-dimensional being of flesh and blood. The other, a flickering pattern of data on a dark, spherical surface. Spaghettification shows us the brutal power of gravity to dismantle the complex. The information paradox hints that maybe gravity also has a secret higher law, one of preservation, written in a language we're only beginning to decipher. The equations say there's a violent change, but we don't have to just imagine it. The universe shows us spaghettification happening on a cosmic scale. Astronomers call these tidal disruption events, TDE. They're the proof, the observational proof for the physics we've been talking about. It happens when a star drifts too close. By chance, too close to a supermassive black hole at the center of its galaxy. The star doesn't get swallowed whole, it gets caught. The black hole's tidal forces stretch it. Compress it, they overcome the star's own gravity. The star is shredded. It becomes a long stream of superheated gas, spiraling inward, and that's not a quiet end. It's the start of a brilliant cosmic firework. The signature is unmistakable. For a brief time, the area around the black hole can outshine its entire galaxy. As the debris forms an accretion disk, the gas is compressed. Heated to millions of degrees, it releases a huge burst of energy, a flare that peaks in ultraviolet and X-ray light. Then the flare fades over months or years as the last of the stellar material is consumed. By watching that light curve, the rise and fall of brightness, astronomers can figure out the black hole's mass, the size of the star that was destroyed. They can test models of how tidal forces work out there. One of the best studied examples is called Assassin 19BT. Spotted in early 2019 by a network of robotic telescopes scanning for sudden changes, the data painted a detailed picture. A star about the size of our Sun had ventured too close to a supermassive black hole. Over 50 million times the Sun's mass, the resulting flare was captured in incredible detail from the earliest moments, a front-row seat to the whole process. Observations from space telescopes like TESS and SWIFT gave a multi-wavelength view. It confirmed the predictions, how the stellar material should behave as it was torn apart and consumed. These events are more than light shows, they're natural laboratories. Each TD is a real-time experiment in extreme gravity. By analyzing the light, astronomers can probe the environment right at the edge of the event horizon. They can measure properties we could never access directly. The rate of these events also tells us about the population, the black holes and stars in galactic centers. It's a way to take a census of the invisible, so we can't send a probe into the abyss, but we can watch as stars become probes for us. Their destruction illuminates the dark. It turns a theoretical process, spaghettification, into an observed phenomenon. We see the universe performing the experiment, confirming that the equations on our pages describe a reality unfolding out there. And if the destruction of something as vast as a star can teach us that much, it makes you wonder, what subtler signals are we missing? What whispers from the edge might be carried not on a blaze of light, but on the fabric of spacetime itself? The singularity is a warning sign, a mathematical scream. General Relativity says at the very center, density becomes infinite, spacetime curvature becomes infinite. And the tidal forces, the ones that spaghettify you, they'd become infinite too. An infinite force that's physics code for we have no idea. Our best classical theory breaks down. It reaches its limit. To understand what happens to that stream of atoms, you have to go beyond Einstein into quantum gravity. That's where the rules change. In the quantum realm, particles aren't tiny balls. They're fuzzy probabilities. They can be in two places at once. They can tunnel. This quantum fuzziness might act as a pressure, a final repulsion that stops matter from crushing into an actual point of infinite density. If that's true, then the infinite stretch from classical physics might never happen. Spaghettification could have a quantum endpoint. Different theories see this end differently. String theory, for instance, says the fundamental ingredients aren't particles, but vibrating strings. And at the heart of a black hole, these strings could tangle into a vast structure, a fuzzball. There's no sharp singularity inside a fuzzball, just a dense, fuzzy ball of stringy energy. If you fell in, you wouldn't be stretched infinitely. You'd merge with this quantum knot. Your information would be scrambled into its pattern, but not erased. Another idea is loop quantum gravity. This says spacetime itself is granular, woven from tiny, finite loops. That granularity might prevent infinite collapse, causing matter to rebound. Like a cosmic bounce, in that case, the stream of your atoms after maximum compression might not end. It could bounce back, emerge somewhere else, maybe into a different part of our universe, or even a separate universe. This is speculative, but it turns the black hole from an ultimate end into a potential gateway. These aren't proven ideas, they're possibilities, but they share a thread. They suggest the classical story of spaghettification, the clean, infinite stretch into nothing, is probably not the full story. At the quantum level, gravity's most violent act might be softened or redirected. The journey of that single file line of atoms might not terminate in oblivion. It might transition into a state or a place our current physics can't yet describe. Exploring this isn't about a happier ending, it's about a complete one. It means our understanding of the cosmos has layers. There's the layer of Newton for planets, the layer of Einstein for black holes right up to the brink, and now we're searching for the next layer, the one that tells us what lies beyond the brink, where spacetime geometry meets quantum probability clouds, and in that meeting, the fate of everything that falls gets rewritten by laws we haven't fully discovered. A quantum end to the stretch resolves the paradox, but there's another idea that the problem never gets a chance to appear. It's a kind of cosmic rule. Roger Penrose called it the cosmic censorship hypothesis. Nature abhors a naked singularity. A singularity is that point of infinite density. Naked means it's visible, exposed, not hidden behind an event horizon. Penrose argued this never happens. The universe always dresses its singularities. It wraps them in the cloak of an event horizon, hiding the place where physics breaks down. It's a firewall of causality, a barrier that shields the predictable universe from the chaos at the core. For the story of falling, this is profound. It means the most violent part of spaghettification, the final approach to that infinite stretch, is a private affair, an interior process no outside observer could witness. The event horizon is a one-way curtain. From our perspective, the laws of physics remain intact. We can calculate orbits, predict gravitational waves, model tidal forces right up to that edge. But the true madness, the singularity itself, is censored, removed from the stage. This isn't just philosophy, it's a practical necessity for doing physics. If naked singularities existed, their unpredictable influence could leak out, cause and effect could break down, the past might not determine the future. Our entire framework for understanding the universe through mathematics would crumble. Cosmic censorship is a hopeful postulate, a bet that the universe, in its deepest extremes, still plays by rules that allow science to function. The debate is ongoing. Some mathematical models for charged or rapidly spinning black holes suggest naked singularities might be possible under very specific conditions. Others argue any realistic, slightly perturbed scenario would inevitably form a horizon, clothing the singularity again. It remains one of the great unsolved conjectures. What does it mean for you falling? If cosmic censorship holds true, your journey has a final, hidden chapter. You cross the horizon, you experience the escalating tidal forces, but the ultimate destination, the singularity, exists in a realm permanently separated. Its infinite nature is something you, and only you, would encounter, and since no information can escape, that encounter remains the universe's ultimate secret. The hypothesis transforms the black hole from a potential portal of chaos into a sealed container. It contains the breakdown of physics, protecting the sanity of the cosmos outside. In doing so, it draws the ultimate line between the knowable and the unknowable, between a universe we can describe and a mystery forever veiled. But the event horizon might not be a door. It could be a wall, and the singularity might not be a point but a surface. The standard black hole model is elegant mathematically, but it's still a theory. And some physicists, in the spirit of science, wonder if we've trapped ourselves with singularities. They propose radical alternatives that get rid of the black hole entirely, at least as we define it. One idea is the Gravastar. Picture a star so dense that its interior isn't crushed matter. It's a bubble of dark energy. That's the energy causing the universe to expand. In this model, the star's immense gravity is balanced by the repulsive pressure from that dark energy core. There's no event horizon. Instead, there's an ultra-thin shell of ordinary matter. A skin holding this strange interior in. If you fell toward a gravastar, you wouldn't be stretched infinitely. You'd collide with that surface. The outcome is still catastrophic, but the story is different. No mysterious one-way passage, just a final, violent impact against the hardest surface in the cosmos. Another proposal is the magnetospheric eternally collapsing object. The MECO, this is an object perpetually on the verge of collapse. It's held up by intense internal radiation pressure and powerful magnetic fields. It would also have a physical surface glowing fiercely, not an event horizon. From a great distance, it would look almost identical to a black hole, a dark shadow surrounded by a brilliant accretion disk. But up close, the absence of an horizon changes everything. In both these models, spaghettification as an endless geometric unraveling doesn't happen. The tidal forces near the surface would still be immense. They would stretch you terribly. But the process would have a definitive endpoint, a boundary, not a coordinate in spacetime you slip past unnoticed, but a tangible, physical limit. These ideas aren't mainstream. The evidence for event horizons is compelling, from gravitational waves to the shadow of M87, but they serve a crucial purpose. They remind us our maps of reality are provisional. The black hole is our best model. It fits a mountain of data, yet it contains a mathematical breakdown inside it, the singularity. Alternative models like Gravastars and MECO try to avoid that breakdown, to craft a picture where physics remains intact all the way to the center. They highlight a profound scientific truth. Our understanding is always a model, a story we tell to explain the observations, and every good story remains open to a revolutionary new chapter. The existence of these alternatives doesn't weaken the standard model. It strengthens the scientific process. It shows a field alive with questioning, willing to imagine a universe where even the darkest giants might have a different, stranger face. The equations tell one story, but there's another story written in culture. That image of spaghettification, it's become this stark, visceral thing in our imagination. A symbol now far beyond the physics journals. It shows up where science meets story. For filmmakers, writers, artists, it's a ready-made metaphor for forces we can't really comprehend. Take Christopher Nolan's Interstellar. That's probably the most famous portrayal. The crew goes near the black hole Gargantua, and you see the tidal forces. The water planet, those huge waves, that's from the black hole's gravity stretching everything. The film takes liberties with time, with what's inside. But the outside, the curvature of spacetime, that's real science. Kip Thorne advised on it, and what you get isn't some cartoon shredding, it's a distortion. Terrifying and beautiful, it communicates the scale, the power, through emotion and imagery, makes the abstract physics feel immediate. In literature, the concept becomes a metaphor. It can be existential dread, the fear of being unraveled by something indifferent to you, or it can be transformation, a deconstruction of the self before maybe being put back together as something new. For storytellers, it's a device for conveying nature's overwhelming power, a power that reduces all complexity, all history, down to a single thread. And that metaphor works because it taps into something intuitive. Everyone's felt stretched too thin, pulled in different directions, compressed by pressure. Spaghettification takes that feeling and projects it onto a cosmic canvas. Artists are drawn to the imagery, too. Visual representations, they range from diagrams to abstract pieces. Some focus on the geometry of stretching, using light and form to evoke warped spacetime. Others use the motif to explore identity, fragility, the dissolution of form against immense power. This cultural reflection, it does more than entertain. It educates by embedding a complex scientific idea inside a narrative or a painting. These works build a bridge. They generate curiosity, make audiences ask about the real science behind the spectacle. They show how extreme physics fuels creativity, provides a new palette of concepts for old human questions. So the journey of this idea from a precise astrophysics term to a cultural touchstone, it shows a dialogue. Science provides the raw material of wonder. Culture shapes it into stories, stories that help us process that wonder. Through that exchange, something as violent and remote as tidal disruption becomes a shared reference. A way to talk about the universe's most formidable forces and our own place within its vast, indifferent, beautifully ordered machinery. The most violent forces in the universe start with a simple idea. A difference in pull. You don't need a black hole to see it. You can use a classroom slinky. Hold it by the top, let it hang, the bottom coils stretch down, pulled by gravity. Then you drop the whole thing. As it falls, something happens. The bottom seems to hover. The top coils rush down to meet it. The slinky compresses. That's tidal forces in miniature. In freefall, the slinky is weightless, but gravity's pull is still a bit stronger on the bottom than the top. That tiny difference causes the compression. It's not spaghettification, but it's the same principle, differential acceleration. The slinky shows how an extended object reacts when gravity doesn't pull evenly. For a clearer picture of stretching, think of a water droplet. In microgravity, on the space station or in a drop tower, a floating water blob is held together by its surface tension. If you place two small masses near it, simulating a gravity gradient, the droplet elongates. It stretches toward the stronger source. It's a direct visual analogy. The water's surface tension fights the stretching pull like molecular bonds in a body would. When the differential pull wins, the droplet tears apart. It's a safe, observable stand-in for a cosmic process. These experiments show students that spaghettification isn't magic, it's mechanics, it's the outcome of a contest. Between the force that holds things together and a difference in gravity that tries to pull them apart, software takes the analogy further. Gravitational simulation programs let you model a cloud of particles falling toward a virtual mass. You adjust parameters, the mass of the central object, the size of the cloud, its initial velocity. Then you watch the cloud, initially a sphere, distorts. It stretches into a long, thin streamer. The simulation visualizes the divergence of geodesics paths through spacetime in a way a slinky or water droplet cannot. It makes the geometry tangible. You see how particles that start close together end up on wildly different trajectories. These tools bridge the gap between a hands-on demonstration and the full mathematical theory. They show the process in its clean, algorithmic form, stripped of atmosphere and heat, revealing the pure geometry of tidal disruption. Each of these teaching tools has its place and its limitations. The slinky demonstrates differential acceleration, but it compresses instead of stretches in freefall. The water droplet shows stretching and disruption, but the forces are surface tension and simulated gravity, not true spacetime curvature. The software shows the geometry perfectly, but it's an abstraction on a screen. The true phenomenon combines all these aspects: immense force, geometric path divergence, and the ultimate failure of material bonds. The analogies are like sketches of a mountain. They capture an angle, a shadow, the general shape, but they can't convey the chilling wind or the sheer scale of the real thing. Yet their value is immense. They turn an unfathomable cosmic event into a series of logical, investigible steps. They let a student ask, what if I change this variable? What if the object is stronger? What if the black hole is bigger? This active questioning is where inspiration lies. It's how an abstract, distant terror becomes an engaging intellectual puzzle. By modeling tidal forces, we don't just teach physics. We invite the next generation to look at the most frightening giants in the cosmos, not with helpless awe, but with the tools of understanding. That shift in perspective, from passive witness to active investigator, may be how we one day solve the deeper mysteries still waiting at the edge of the dark. Every stretch and squeeze lets energy out. Those huge tidal forces, when they deform matter, they're doing work. They're fighting atomic bonds, molecular structure, the object's own integrity. And that work doesn't just disappear, it has to go somewhere. In the physics of falling, it becomes heat, a staggering amount of heat, As something is spaghettified, the violent friction between its own layers, the compression of gases, the sheer mechanical energy of being torn apart, all of it turns into thermal energy. Temperatures can jump to millions of degrees instantly. That's why the aftermath isn't dark, it's a brilliant flare. The shredded stellar material, now a superheated plasma, radiates that energy away as light. X-rays, gamma rays ablaze across the spectrum. The black hole's feast becomes a beacon. This heating is a direct thermodynamic consequence of the deformation. It's the universe balancing the books. The gravitational potential energy of the infalling matter gets converted first into kinetic energy, the speed of the fall. Then, through the violent, dissipative process of tidal shredding, that kinetic energy transforms into internal thermal energy. The matter isn't just stretched. It's cooked, and that thermal energy is what powers the radiation we see from accretion disks. Those luminous halos around black holes are essentially the glow of spaghettified matter, heated to incandescence by its own destruction. The disk is a continuous engine of this. Fresh matter gets tidally stretched as it spirals in, heated by friction and compression, radiating furiously, and finally crosses the horizon, having given up much of its energy to the universe as light. This connects to one of the most profound ideas in black hole physics: entropy. In thermodynamics, entropy is disorder. A broken cup has higher entropy than a whole one. A gas spreading out has higher entropy than one confined. Spaghettification creates the ultimate disordered state. A complex, structured object becomes a chaotic, high-energy stream of particles. Its entropy skyrockets. Jacob Bekenstein and Stephen Hawking showed that black holes themselves possess entropy, and it's enormous. It's proportional to the area of their event horizon. This black hole entropy is now thought to be deeply connected to the quantum information of everything that's fallen in. So the thermodynamic journey is clear. An ordered star falls in. Tidal forces perform work, increasing disorder, generating heat and radiation. The resulting high-entropy stream adds to the black hole's total entropy, which is recorded on its horizon. The process is a direct pipeline from order to disorder, from gravitational potential to radiant heat, with spaghettification as the violent, essential transformer in the middle. It frames these objects not as passive drains but as active participants. They are converters, taking in ordered mass and releasing disordered energy, powering some of the most luminous phenomena we see. The atoms are on their final approach now. The singularity is ahead, but for the particles themselves, first the atoms are torn apart. The tidal forces overcome the electromagnetic force. The atoms are ionized, stripped down to bare nuclei and free electrons, but the journey continues. The nuclei have their own structure, protons and neutrons bound by the strong force. And as the gravitational gradient steepens, even that force is overcome. The nuclei dissociate. They break into their constituent quarks and gluons. What was a person, then a strand of atoms, becomes a dense, hot soup of fundamental particles, a quark-gluon plasma, moving single file toward the center. But can it go further? Can the particles themselves be torn apart? In our current physics, electrons and quarks are point-like, fundamental. They have no smaller parts. But at these extremes, the concept of a particle might lose meaning. We enter a realm of speculation governed by the Planck scale, the universe's smallest possible unit of measurement. A length 1,000,000 billion times smaller than a proton. At this scale, the smooth continuum of spacetime breaks down. It becomes grainy, foamy, quantum. The density here is the Planck density, a number so vast it defies analogy, about 10 to the 96 kilograms per cubic meter. This isn't just high density. It's the density where gravity itself must be described by quantum mechanics. This is the ultimate frontier, not just the end of matter, but the end of spacetime as a reliable stage. The geometry that stretched the particles into a line becomes unstable. The concepts of here and now dissolve into quantum probability. In this final moment, the spaghettified stream doesn't hit a wall. It reaches a domain where our language of location and substance fails. The particles don't vanish. They transition into a state our theories cannot describe. And this leads to the core mystery, the final question: does everything get crushed into a dimensionless point of infinite density, or does the extreme warping create a passage? Some theories in quantum gravity suggest the singularity might not be an end but a bridge, a wormhole throat, or a bounce into a new region of spacetime. In those models, the stream of particles might not terminate. It might be transposed, its information scrambled, reconfigured, emerging somewhere else entirely. Another time, another universe, or a part of our own cosmos far removed. We don't know, and perhaps we can never know from outside, but the progression is clear. From structure to atoms to nuclei to a quantum foam at the edge of reality, the journey is a relentless peeling away of layers, a reduction to the most basic ingredients. And then a step beyond, into the unknown laws that govern when the fabric of the cosmos itself is frayed. That final quantum foam might not be the end. The math in Einstein's equations, it's symmetrical. Time is just another dimension. And if you follow that symmetry all the way, a black hole solution can be extended. It can connect to another place or another time. That's the realm of Einstein-Rosen bridges, wormholes. So imagine the deepest part of the funnel, not as a dead end, but as the narrowest point of a tunnel. A throat on the other side. The equations show the tunnel could flare out again, not into our universe, but into another region of space-time. It could connect to a white hole. A white hole is the theoretical opposite. If nothing can escape a black hole, nothing can enter a white hole. It would be a source, matter and energy, erupting from a singularity. A fountain of space-time instead of a drain. In this picture, that spaghettified stream of particles, after the quantum chaos at the center, might get ejected from a white hole somewhere else. Your journey would be a transformation from a complex being to a stream of fundamental ingredients to a reassembled burst of energy in another cosmos. It's a breathtaking idea that the most destructive process could be a gateway, a cosmic recycling plant, but there's a catch, a monumental one. These theoretical tunnels are unstable. The moment any matter tries to pass through, like our stream of particles, the wormhole throat would pinch off. It collapses faster than light could cross it. To hold it open, to make it traversable, you'd need something with negative energy density, something that creates a repulsive gravity. Physicists call it exotic matter. We have hints of similar effects, like the Casimir effect in quantum theory, but nothing on the scale needed. Nothing to prop open a wormhole large enough for anything to pass. So the geometry permits these bridges in theory, but nature likely forbids them in practice. Yet the idea persists. It fuels our deepest stories of travel and transformation. It represents a hope embedded in the math that the universe is connected in ways we can't yet see, that even in the heart of darkness there might be a thread leading out. This speculation, it's far from proven science, but it completes an arc. It asks if spaghettification is truly the end of the story, or just the most dramatic chapter in a longer, stranger journey across reality itself. The equations give you the shape, but to see the story move, you need a different eye, a digital one. Our picture of spaghettification now is made of pixels and plasma. It comes from supercomputers running incredibly complex code. That's computational astrophysics. It turns abstract equations into moving visuals. It lets you watch, in a virtual space, what happens when a star or a gas stream meets the tidal force of a black hole. The process isn't just gravity. It's fluid dynamics, magnetic fields, radiation, shock waves, all interacting in an extreme place. To model that, scientists use numerical simulations. They break the falling material into millions, even billions, of pieces, simulated particles or grid cells. The computer calculates how each piece moves, heats up, interacts with others under the black hole's gravity. One key framework is magnetohydrodynamics, MHD. It models how electrically conducting fluids behave when they're threaded with magnetic fields, fluids like the superheated plasma from a shredded star. These fields aren't passive. They get stretched and twisted by the black hole's spin and the swirling disk. They can channel material, accelerate jets, transfer energy in ways gravity alone can't explain. The same codes that helped make the theoretical images for the Event Horizon Telescope, the one that captured the shadow of M87's black hole, they are also used to simulate tidal disruption events. Researchers can input a black hole's mass, a star's size and composition, and start the simulation. What plays out on screen is a violent ballet. You see the star stretch into a long, thin ribbon. You watch self-gravity cause the ribbon to fragment. You witness debris colliding, heating to incredible temperatures, forming a luminous, chaotic disk. These simulations aren't just movies, they're predictive tools. By running thousands of them with slightly different starting points, astrophysicists build a library of possible outcomes. They can then compare these virtual light curves and emission patterns with actual data from telescopes observing real events. When a simulation's prediction matches an observation, it validates the physics. It tells us our models of gravity, plasma, radiation are on track. This loop theory, simulation, observation, refinement, that's the engine of modern discovery. It shows a fundamental truth. Today's astrophysics isn't just telescopes and equations on a board. It's a triad: deep theory, massive computational power, and precise observation, all working together. The supercomputer simulation is the crucial bridge. It takes the clean, idealized world of Einstein's equations and marries it to the messy, turbulent, magnetized reality of cosmic matter. Through this digital lens, spaghettification changes from a stark concept into a rich, dynamic process. You see not just a strand, but the storm that creates it. And that detailed vision brings us closer to the next question. If we can simulate the destruction so accurately, could we ever simulate what happens to the information that's lost? The unraveling isn't just a physical thing. It asks a basic question: what makes something itself? When your bonds break, when your pattern gets pulled into a line, do you stop existing? Or is that pattern just changed, put into a completely different state? This is where physics runs into an old puzzle. The ship of Theseus. A ship sails, and over the years, every piece is replaced. Every plank, every nail. When the last original part is gone, is it the same ship? And if you took all the old parts, the discarded ones, and rebuilt a ship from them, which one is the real one? It's about identity, what it is over time through change. Is identity the material, or is it the pattern, the arrangement of that material? Spaghettification is the most extreme version of this. Here, it's not just replacing planks, it's taking the whole ship apart into sawdust, and then pouring that sawdust into a fast river, one grain at a time, in a single file. The original arrangement, the pattern that was a ship or a person, is completely scrambled. It looks destroyed. From our human perspective, that's the definition of destruction. The coherent self is gone, but physics, quantum physics and information theory suggest something else. It whispers that the information, the data of that pattern, might not be destroyed. We mentioned it before, it might be preserved in a wildly scrambled form, on the event horizon, or in some quantum description of the inside. If that information persists, then in a data sense, the identity isn't erased. It's encrypted, translated into a cosmic code on the surface of a black hole, or into the state of a fuzzball. You're no longer a thinking being, you're a string of data. In the universe's most secure ledger, this forces a choice in perspective. from the inside, from the experience of the person falling, the process ends. It ends in dissolution. The conscious self, which needs a specific biological structure, is extinguished. That story ends. From the outside, from a cosmic, informational view, the story continues. But in a form that's utterly alien, inaccessible. So which perspective is true for identity? Is identity the first-person experience, or is it the underlying mathematical truth of the system? These aren't just abstract thoughts. They change how we see the universe's most violent acts. If information is truly conserved, then transformation might be the fundamental rule. Not annihilation. A star, shredded into a glowing stream, feeds a galaxy with its light. Its material becomes part of new worlds. Its information, in some form, endures. In the grandest view, spaghettification isn't an end. It's a metamorphosis, a forcing of the complex into the simple, so that it might become part of something else. In the vast cycling processes of the cosmos, the you that thinks and feels is lost, but the atoms that were you, and the quantum information that arranged them, they continue. On a journey whose final chapters are written in laws we haven't fully read yet. That line of thinking about information lasting, it brings up a bigger question. If the universe doesn't destroy things but changes them, then where is everybody? That's the Fermi paradox. The galaxy is old, billions of stars, probably planets. Life should have started many times, intelligent life too. The sky should be full of signals, of artifacts, but we hear nothing. It's silent. One idea is the great filter. A barrier so tough almost no civilization gets past it. We usually think of filters we make ourselves: war, environmental collapse, technology backfiring. But what if the filter is just out there, waiting? A natural hazard so common and so final it resets everything. Black holes could be that, not as something that hunts, but as a permanent part of the galaxy. A cosmic minefield. Think about the timescales. A technological civilization lasting a few thousand years is a flicker, but its curiosity, its drive to explore, that could go on for eons. If it develops interstellar travel, even slow travel, its probes would eventually cross huge distances. The galaxy has stellar mass black holes, leftovers from dead stars. They're dark, nearly invisible except by how they bend light a little. A ship on a long journey, using gravity assists or navigating by star maps, could miscalculate. Could drift too close to a gravity well you can't see. The result isn't a crash, not in the usual way. It's spaghettification, a quick, quiet unraveling. No explosion, no debris, just a stream of atoms added to the black hole. From the civilization that sent it, the probe just vanishes, goes silent, a mystery. Now scale that up. Think of a civilization itself, one that's mastered energy, building huge structures, a Dyson sphere or a ring world. What if their engineering failed catastrophically and nudged their star's orbit? Sent it drifting toward the supermassive black hole at the galaxy's center. The end wouldn't be fire, it would be a stretch. The whole stellar system, over centuries, getting tidally shredded. That civilization's works, its history, its people, all turned into a bright, short-lived flare in the accretion disk. A final, brilliant signature that fades into the background noise. This is a speculative answer to the great silence, that the universe isn't hostile, it's indifferent. And its indifference contains physics so extreme that curiosity becomes a lethal risk. The black hole doesn't hunt, it just is, and by just being, it acts as a sieve, filtering out those who go too far or whose home systems drift into the wrong path. It's a reminder, for all our intelligence, we're moving through a realm built by forces that don't compromise, where a single misstep across all that space and time can have consequences written in geometry, not in malice. This line of thinking, it's conjecture, but it reframes our place. It suggests that surviving, maybe thriving, in the cosmos isn't just about mastering our own world. It's about learning to read the invisible contours of gravity, to map the pits and slopes of spacetime with extreme care, because the silence out there might not mean we're alone. It might be a lesson echoing across the light years, a lesson written in tides and in strands. Space isn't silent. It has a hum, a vibration we're just starting to hear. The story of falling, of being stretched into a strand, doesn't end when the light fades. That violent change, the spaghettification itself, sends out a different signal. A tremor in reality, a gravitational wave, and we're building observatories to listen for the echoes of matter being torn apart. Think of the most extreme tidal disruption. A star shredded not by a supermassive black hole, but by a smaller, denser one, or the final moments before two neutron stars collide and merge. These catastrophes aren't smooth. They're messy, lopsided, violently dynamic, as the star stretches into a stream, or as the neutron stars spiral and deform. Their asymmetrical motion churns the spacetime around them. That churning creates ripples. These ripples are gravitational waves. They move outward at light speed, carrying a direct imprint of the chaos. Today's detectors, like LIGO and Virgo, opened this window. They've heard the chirp of black holes merging, but to catch the more complex song of a tidal disruption, we need to go to space. We need an observatory free from Earth seismic noise. That's LISA mission, the Laser Interferometer Space Antenna, planned for the 2030s. 3 spacecraft in a vast triangular formation, millions of kilometers apart, connected by lasers. It will detect gravitational waves at much lower frequencies, the perfect band to listen for the protracted, ringing signal of a star being stretched apart over hours or days. The signal would be unique, not a clean chirp but a rising cacophony, a complex waveform that encodes the star's structure, the black hole's spin, the brutal geometry of the tidal forces. Scientists call it the gravitational wave asteroseismology of a dying star. It would be the sound of spaghettification, and LISA might detect the final splash too. The moment the last of the disrupted matter crosses the event horizon, that moment when the stream of atoms finally vanishes could create a distinct, damped ringing in the gravitational field. A direct probe of the horizon itself. This is a fundamental shift. For centuries, astronomy was the science of light. We looked, now we're learning to listen. To put our ear to the fabric of spacetime and hear the events light cannot escape from. A tidal disruption flare gives us the afterglow, the thermal radiation from heated debris. But the gravitational waves give us the dynamics, the real-time physics of the tearing itself. They're a more direct messenger from the edge. Hearing these events would do more than confirm a theory. It would let us weigh the black hole with precision, measure its spin, understand the internal composition of the star that fell victim. It would turn a spectacular light show into a precise laboratory measurement of extreme gravity. We'd move from watching the shadow on the wall of the cave to feeling the vibrations of the objects casting the shadows. The future of understanding these dark giants lies in a richer symphony of data, where the silent unraveling of a star finally finds its voice in the ringing of spacetime. The silence we listen for and the violence we calculate, it exists in a universe that also lets us do the listening. And you have to ask why. The laws that allow a black hole's crushing singularity are the same laws that allow the fragile chemistry of a brain. That's not a coincidence you can ignore. It points to something, a cosmic perspective, the Anthropic Principle. In its simplest form, it says the universe we observe has to be compatible with us being here to observe it. We see certain constants, the strength of gravity, the mass of an electron, because if they were even slightly different, we wouldn't be here to see them. You think about the fine-tuning. Gravity is weak enough that stars burn for billions of years, letting planets form and life evolve. But it's also strong enough to collapse massive stars into black holes. And the same nuclear forces that forge carbon in stellar cores, the element for life, they also govern the final moments of a supernova that creates those black holes. The cosmic ledger is balanced on a razor's edge. If gravity were stronger, stars would burn out too fast. If the electromagnetic force were weaker, atoms wouldn't hold together. There'd be no stable matter to build a planet or a person, and crucially, no long-lived stars whose deaths create the black holes we study. This puts spaghettification in a new light. It's not an arbitrary horror. It's a specific, inevitable outcome of a set of physical laws that also make curiosity possible. The tidal forces that shred a star are a direct expression of the gravitational constant, a number that, if changed, would erase galaxies, solar systems, biologists. Our ability to model this, to simulate it and wonder about its meaning, is itself a product of that same cosmic recipe. So when we contemplate falling into the abyss, we're engaging in an act the universe's own parameters have made possible. The darkness we study is woven from the same fabric as the light of understanding. That doesn't give the violence a comforting purpose, but it frames it as part of a coherent whole. A universe without black holes might be a universe without the heavy elements that make up our world. A universe without the extreme physics of tidal forces might be a universe too simple, too bland, to generate any complexity at all. The Anthropic Principle isn't an explanation. It's a reminder of context. We find ourselves in a cosmos capable of breathtaking beauty and terrifying indifference. The fact that we can stand at this crossroads, measuring the tidal forces that would unravel us and pondering the information they might erase, that's perhaps the most remarkable datum of all. It suggests that in this vast, finely tuned arena, observation itself is a rare feature. Our questions about the edge are, in a deep sense, the universe beginning to understand its own strange rules. That cosmic perspective, it grounds us here. The same forces that shape those distant events, they shape our own explorations. The physics that spaghettifies a star, it's not just a destructive curiosity. It's a fundamental rule, a rule of orbital mechanics, one we work with every time we send a craft beyond Earth. Now, engineers aren't facing the steep gradients of a black hole. But they do contend with the gentle, persistent tug of tidal forces, and they've learned to use them. This is the practical side of the principle, harnessing the difference in gravity. To stabilize, to power, to reveal, consider a spacecraft in orbit. It's not a single point, it has length. The end closer to Earth feels a slightly stronger pull than the end farther away. This tiny difference creates a torque, a twisting force. If it's unchecked, it can cause the craft to tumble, but engineers can turn this problem into a solution. They design some satellites with long booms. The tidal force naturally wants to align that long axis with the direction of gravity, like a compass needle pointing down. This passive alignment is called gravity gradient stabilization. It's a clever, fuel-free way to keep a satellite's instruments pointed at Earth, using the same differential pull that, in a far more extreme environment, would tear it apart. Looking further ahead, this concept underpins one of the grandest ideas in future engineering, the space elevator. The vision is a cable, anchored on Earth and extending tens of thousands of kilometers into space. With a counterweight at the far end, the entire structure is a delicate balance between two forces. Earth's gravity pulls down on the lower sections. The centrifugal force from Earth's rotation pulls outward on the upper sections and the counterweight. The difference in these forces along the cable's length, that's a tidal force. And that difference is what provides the tension that holds the structure taut, designing a material strong enough to withstand that incredible tensile stress. From the crushing gravity at the base to the outward pull at the top, that's the monumental challenge. It's an engineering problem defined by the very gradient we've been exploring. To build a bridge to orbit, we must master the same physics that creates a cosmic strand. This understanding also illuminates worlds in our own solar system. Take Jupiter's moon Europa or Saturn's moon Enceladus. These icy shells hide vast subsurface oceans. They are not warm from the sun, they are far too distant. Their heat comes from within, generated by tidal forces. As these moons orbit their giant planets in slightly elliptical paths, the gravitational pull they feel changes. They are flexed, stretched, and squeezed with each orbit. This constant tidal kneading generates friction deep inside their rocky cores. That friction produces heat. Enough to melt ice, enough to maintain global oceans of liquid water. The plumes of water vapor and ice crystals erupting from Enceladus's south pole, they are a direct testament to this power. The same physics that could, in another context, shred a world, here acts as a subterranean furnace, creating potential havens for life in the cold outer solar system. So the journey from a black hole's edge to a moon's hidden sea is connected by a single thread of physics. The terrifying gradient that spells doom in one realm becomes, in another, a tool for stability. A design constraint for ambition, or a hidden engine for geological activity. It reminds us the universe's rules are consistent, scaling from the catastrophic to the constructive. Our grasp of the extreme sharpens our ability to navigate the subtle, turning a force of dissolution into a principle we can use to explore, to build, and to understand the hidden warmth in distant, frozen worlds. The equations give us a map, but the center, that's still marked, here be dragons. We've described the journey. The stretching, the squeeze, the transformation into a cosmic strand. And yet, with all that, profound mysteries remain. They're shimmering just beyond our understanding. These aren't failures, they're signposts, the open frontiers that keep physicists awake at night, dreaming of new mathematics, peering into new data. The story of spaghettification is still being written. Its final chapters hinge on questions we can't yet fully answer. First, the singularity. What is it truly? In the equations, it's a point, infinite density, infinite curvature, a place where the laws of physics stop giving sensible answers. But does nature actually permit that? Or is the singularity a signal, a sign that Einstein's beautiful theory of gravity, while spectacularly successful, is incomplete? Most researchers believe it's the latter. The singularity is likely not a real physical object. It's a mathematical placeholder, a sign that we need a theory of quantum gravity for when matter is compressed to the smallest possible scales. At that point, the very concepts of point and density might lose their meaning, replaced by something stranger, a quantum foam, a fuzzball, a cosmic bounce. The true nature of that central point, or the lack of one, is the ultimate mystery at the heart of the darkness, and that leads directly to the second great question. How does quantum gravity alter the final moments of the fall? The classical description says the tidal forces become infinite, stretching the stream of particles into an infinitely long, infinitely thin line. But quantum mechanics abhors infinities. It introduces uncertainty, fuzziness, discrete packets of energy. In a quantum description, that infinite stretch might be capped. The spaghettification process might reach a maximum, and then something else. Perhaps the particles undergo a quantum phase transition. Maybe they tunnel into a different state of existence. We simply don't have the complete theory, not for the last instance before the classical singularity. That moment remains the most extreme environment conceivable. A laboratory for laws we haven't discovered yet. Then there's the paradox of information. When an object is tidally shredded, scrambled into a one-dimensional stream, and lost behind the horizon, is the information about its original form destroyed forever? Quantum mechanics says no. General relativity, in its classical form, suggests yes. This conflict is one of the most heated debates in theoretical physics. Solutions like the holographic principle, where information is stored on the event horizon, or ideas like firewalls and replica wormholes, are bold attempts to resolve it. But a definitive answer, one that can be tested, remains elusive. The fate of information isn't just a technical puzzle. It strikes at the core of whether the universe is fundamentally predictable and reversible, or whether some processes truly erase the past. And this brings us to a final speculative wonder. Can anything ever emerge from a black hole? We've thought of them as the ultimate one-way doors, but what if some part of that spaghettified stream, its information or its energy, can find a way out? Not through the classical event horizon, but through quantum processes like Hawking radiation. This incredibly slow evaporation, predicted by Stephen Hawking, suggests black holes are not entirely black. They can slowly leak energy and with it perhaps scrambled information, or consider the wilder possibilities, wormholes, white holes, theoretical exits from the gravitational trap. While these are mathematically speculative and likely unstable, they keep alive a profound question. Is total absorption the only possible ending? Or does the cosmos, in its deepest workings, always leave a thread? However faint, connecting what goes into what might come out, these unanswered questions are not a wall, they are a horizon. They define the expanding edge of human knowledge. Each one is a beacon, guiding the next generation of telescopes, particle colliders, and thought experiments. The mystery of what happens in that final descent beyond the stretch, beyond the squeeze, ensures that the story of falling into a black hole remains the greatest unfinished tale in all of physics. It's a story whose next pages are being written right now, in equations on whiteboards and in data from the edge of the visible universe. The force that tears a star apart also shapes its galaxy. You have to pull back to see it, way back, from one object falling into the life of 100 billion stars. Spaghettification isn't just some horror show. It's a kind of regulation, a key part of how the universe works. It starts at the center with the supermassive black hole. That dark thing, millions of times heavier than our sun, sits in the heart of almost every big galaxy. It's not just sitting there, it's an engine, and it runs on tidally shredded matter. When a star or a gas cloud gets too close, it gets stretched, compressed. That tidal disruption makes a bright flare, a swirling disk, but the energy released does more than make light. It has consequences. The intense radiation, the magnetic jets shooting from the black hole's poles, they act as a feedback system. They blast outward into the galaxy. That energy heats up huge amounts of interstellar gas. It can push the gas away or stir it up, and by doing that, it regulates the birth of new stars. Stars form when cool, dense gas clouds collapse. If the gas is too hot, too stirred up by these outflows, it can't condense. So the black hole, feeding through spaghettification, puts a limit on its own galaxy's growth. It stops runaway star formation. It keeps a balance. In some galaxies, this gets so extreme it shuts down star birth completely. That's a red and dead elliptical galaxy. In others, like our Milky Way, it's a gentler modulation. The monster at the center, fed by tidal destruction, acts like a governor, a thermostat for the stellar nursery. That matter isn't just destroyed, it's transformed, redistributed. The atoms from a shredded star get heated, ionized, accelerated. Some fall past the event horizon, adding to the black hole's mass. But a lot of it gets flung back out into the galaxy by those jets and winds. These outflows are full of heavy elements, stuff forged in stellar cores and supernova. They seed the space between stars with the raw materials for new planets, for life. The calcium in your bones, the iron in your blood, some of those atoms might have once been part of a star that was torn apart, ejected in a galactic wind, and then ended up in the cloud that formed our solar system. From this view, the process changes. It's not just a destructive end, it's part of a big cyclical economy, matter and energy, a star dies, and its remains might get pulled toward the central black hole. There, tidal forces process it. Its energy is released, shaping the galaxy around it. Its elements are scattered, destined for future stars and worlds. It's a cosmic death and rebirth on a scale that's hard to grasp. This reframes spaghettification. For an individual, it's an absolute end. For the cosmos, it's a necessary step. A step in an endless dance. The same physics that turns a complex being into a stream of particles also makes sure galaxies don't burn too bright or too fast. It helps create the stable, long-lived environments where solar systems can form, where life can arise. So when we look at the silent black hole at our galaxy's center, we're not just looking at a potential doom. We're looking at the quiet heart of an ecosystem that, through forces of unbelievable power, helped make our existence possible. The fall is a story told by physics. It starts from far away, where you're just an object in orbit. Your path is a slow spiral following the pull of gravity. But as you get closer, the curve of spacetime itself becomes the main thing. The gentle slope turns into a steep drop. You're not orbiting anymore, you're falling down a well, and the sides get steeper with every meter. The first real sign is a faint pull, a difference between your head and your feet. That's the tidal force. For a long time, it's just a background hum. But the math is strict. That force grows with the cube of how close you are. It doesn't rise slowly. It explodes. A whisper becomes a shout, then a scream. Long before you see any boundary, if the black hole is small, that force tears apart the bonds holding your molecules together. Your story as a coherent thing ends right there. You become plasma, streamers of light. If you're falling into a supermassive black hole, the story changes. You cross the event horizon without feeling it. In your own frame, nothing special happens at that moment, but the rules of what you can see have shifted. All possible paths for light now point inward. Escape isn't just hard, it's forbidden by geometry. The entire outside universe gets compressed into a bright disk above you. Then it narrows to a point, and then it's gone. You are inside. The silence is total. Now, deep in the interior, the tidal forces you avoided earlier finally arrive. The stretching begins in earnest. Spacetime itself pulls your head and feet apart along diverging paths. At the same time, compression squeezes you from all sides. It's a cosmic vise. This is spaghettification, and that work generates heat, immense heat. Your form, now a stream of particles, glows with thermal energy. It radiates X-rays. That radiation is the last signal of your mass's energy, shed before it crosses the final threshold. The last part of the story is the singularity. In the classical view, it's the end. Tidal forces would grow toward infinity, stretching particles into an infinitely thin thread before reaching a point of infinite density. But that's where our current story stops, on a cliffhanger of mathematical infinities. They're a signal that the narrative needs a new author: quantum gravity. Einstein's laws step back here. They suggest the end isn't a point but a transition into a realm where particles become probabilities, where space-time becomes a granular foam. The fall might not end with erasure but with translation into a language of physics we're still learning to read. The final verses of this epic haven't been written yet. They're waiting in the quantum silence at the bottom of the world. That silence at the bottom of the world, it's not a full stop, it's a question, and it's already pulling the next explorers. Not with ships, but with equations, with engineering. The need to understand spaghettification, to see it happen out there, that's becoming a blueprint for how we'll explore space. It's a puzzle so compelling it's actually designing the tools we'll use to see the universe again, but new. Our own galactic center has the prime target. Sagittarius, a star, that supermassive black hole. It's our closest giant, a natural laboratory 26,000 light-years away. To go from a blurry image to a detailed movie of that chaotic edge, we have to go bigger. We have to think in orbits. The next step is the Event Horizon Explorer, a proposed space telescope. It would work together with ground arrays like the ones that got that first shadow. By putting a radio telescope in space, you create a virtual dish as large as Earth's orbit. The resolution would be staggering. You could potentially see the turbulent flow of matter. Right at the event horizon's edge, you could watch magnetic field lines snap and reconnect, see the real-time dynamics of the accretion disk where the tidal forces start their work. This isn't just a better picture, it's a physics instrument. It would test if the spacetime around Sagittarius, a star, matches Einstein's predictions for a spinning black hole. With a precision we've never had, any tiny deviation in the shadow's shape or in the disk's swirl could be a clue, a hint of new physics, and alongside this, a new fleet of survey telescopes is coming. The Vera C. Rubin Observatory. It has a gigantic mirror, an enormous field of view. It will scan the entire southern sky every few nights. It's built to catch change. And tidal disruption events, those brilliant flares from shredded stars, they're fleeting. The Rubin Observatory is predicted to find thousands of them. Every year, an avalanche of data. Each flare is its own experiment, a different type of star, a different approach angle, a different black hole mass. By collecting this vast library of cosmic disruptions, astronomers can classify them, understand the full range of how gravity takes a star apart. They'll see the outliers, the strange events that don't fit the models, and those are often the portals to new discovery. But raw data isn't enough. The signals from these events are buried in noise. The physics is too complex for simple intuition, so the quest becomes interdisciplinary. It demands a new kind of scientist. The astrophysicist now also has to be a data architect, working with machine learning algorithms to sift through petabytes of telescope images to find the subtle signature of a distant star being stretched. The theorist has to collaborate with computational experts, using the world's most powerful supercomputers to run magnetohydrodynamic simulations that include general relativity, plasma physics, radiation transport. These simulations are the testing ground. They let us play out millions of scenarios to see which one matches the flickering light of a real tidal disruption event. Billions of light years away, the engineering challenge mirrors the scientific one. To build the Event Horizon Explorer, we need to master formation flying in space. With nanometer precision, to process the data from the Rubin Observatory, we need to advance data storage and network infrastructure on a global scale. This drive to see spaghettification in action, it's pushing the boundaries of what's technically possible. It's inspiring students in mathematics, in computer science, in aerospace engineering to turn their skills toward the deepest questions. They aren't just building tools, they're building the eyes and ears for a civilization that wants to listen. To the gravity of the cosmos, this convergence is the real inspiration. Understanding how things fall apart is driving us to come together, to combine disciplines, to invent new technologies, to train a generation of thinkers comfortable in the gray area between abstract theory and hard, observational fact, the mystery of the strand. It's more than a cosmic curiosity. It's a catalyst forcing innovation, forcing collaboration, forcing a clearer vision of our place in a universe that is both destructively simple and infinitely complex. The equations give us a map, but the territory is a place of unimaginable power. We're here on a small rocky world, held by the gravity of a modest star. Our lives are decades long. Our concerns are often what we can see, and yet with our minds we've reached across the void. We've deduced forces that would annihilate us instantly. We've written the rules for how a star is torn into luminous streamers. There's a disconnect in that, and a connection. To understand spaghettification is to hold two truths. One is the absolute, impersonal violence of the cosmos, a violence that isn't malicious. It's a consequence of geometry and mass. It's a universe where structures, no matter how grand, are temporary. Given enough time, gravity simplifies them, reduces them to basic parts. That truth can feel chilling, a reminder of our fragility against eternity. But the second truth is that we can know this. That a species that evolved on savannas can, through observation and imagination, reconstruct the final moments of matter falling into an invisible pit millions of light years away. We're not just witnesses, we're interpreters. The laws that govern those destructive extremes are the same laws that let our planet exist, let our sun shine. Let our minds reason. Our curiosity isn't an accident. It's a feature of a cosmos complex enough to generate beings who ask about its origins. This journey from our world to the edge of a black hole and back fosters a specific humility. Not the humility of insignificance, the humility of perspective. It shows us our home is a rare bubble of calm in a sea of extreme phenomena, the stable gravity that lets us walk. The thin atmosphere that shields us, the steady star that warms us, these aren't universal defaults. They're precious local conditions. Understanding the fury elsewhere makes the peace of our own corner not a given, but a gift to be recognized. So the study of terrifying physics becomes a deeply humanizing endeavor. It's a testament to our need to look into the dark and not just fear it, but to learn its name. To chart its contours, to hear, in the silent mathematics, the story it has to tell. That urge to comprehend, to push the boundaries, is one of our finest traits. It transforms cosmic violence from a spectacle into a source of awe at the scale of the forces, and awe at the quiet intellect that can, from this distant vantage, begin to understand them. We are both tiny and enormous, fleeting and eternal in our quest for light. Our place in this violent universe is not as victims, but as the part that has become conscious of the whole. And in that consciousness, we find a connection to the cosmos more enduring than any strand of matter. It's the connection of understanding, a silent conversation between the mind and the abyss that continues with every question we dare to ask. What started as a whimsical name, Spaghettification, turns out to be a kind of cosmic signature. It's more than physics, it's a way of seeing. We followed gravity's ultimate stretch. From the silent event horizon all the way to that quantum whisper at the edge of the singularity, we saw it shape galaxies, fuel the birth of stars. It challenges the laws we use to describe reality. This process is so violent in its details, but it's a universal sculptor. It shows us the cosmos operates on a scale of power and subtlety that tests our imagination. Constantly, there's that famous saying, the universe isn't just stranger than we imagine, it's stranger than we can imagine. Our theories are maps, and black holes show us where the maps end. Where the true wilderness begins, that wilderness isn't a place of fear, it's a place of potential. Every unanswered question about information, every mystery of the quantum interior. It's an invitation, a call to the next generation, to the thinkers and the observers and the dreamers. Let this exploration be a spark, a reminder to look up at the dark spaces between the stars. To see not emptiness but a frontier, stories waiting to be decoded, that human drive to explore, to understand our place in this vast and often violent tapestry. That drive is itself a force of nature. If you've enjoyed this journey to the edge of understanding, there are more mysteries waiting. You can subscribe for future voyages into the unknown. And we'd love to hear your thoughts. What about black holes captivates you? What puzzles you the most? Share your questions in the comments. Until next time, keep looking up. Stay curious.